Okay.
That's fine. Yeah, that's great. Thank you.
Okay, so tonight's all about technology, really, technology through the ages. And let's start off in the very beginning, before telescopes or anything else like that. And actually, people had made really good progress on this. I mean, by 700 BC, the Babylonians and Egyptians had worked out the Saros cycle of the 18-year eclipse cycle. Now, I think that's absolutely fabulous. And so they knew about constellations, they knew about the five naked eye planets, and so astronomy was in a good position altogether. It was politically very advantageous as well. It culminated really in the Greeks and Ptolemy. And Ptolemy produced the Almagest, which essentially mapped out the sky, and it was a cosmological model, and it was based on a real philosophy. It was based on uniform motion in a circle. It was based upon the four essences, earth, fire, air, and water, plus the quintessence, the non-changing stellar sky, the universe beyond it. And of course, the earth was at the center. And so this cosmology lasted for 1200 years or more. And effectively, what it did was it predicted where you would find the naked eye planets. So it was an almanac which you could go and test. And this is where it started going wrong, because clearly, when you started plotting the things, particularly for Mars, things didn't work out at all. And so the beautiful, simple, original model that Ptolemy had built, he then had to add lots and lots of fudge factors like epicycles and adherents, etc. And so the model got more and more complex. And in science, that usually means it's going to be wrong. And so along came in 1543 Copernicus, and he made a major shift. Instead of having a geocentric universe with the Earth stationary at the center, he had a heliocentric universe with the sun at the center and the Earth and all the naked eye planets going around it. Except it wasn't really any more successful at predicting planetary positions than Ptolemy's was, mainly because he'd used circular orbits. And so following on from there, we have Tycho Brahe and Kepler. Now, Tycho Brahe was the last of the great observers before telescopes came along. And he had a big quadrant arc which plotted the positions very accurately too, much better than an arc minute of scale. And particularly the orbit of Mars. And as many of you will know, if you plot Mars in the sky, it goes from right to left, and then it stops and goes back to the right again, then it stops again, then it goes left again. And so, and it does vice versa as well. It goes left to right, then back again. So it does retrograde loops on the sky, and it's very hard to predict those. And the answer came out with Kepler in about 1605 to 1610. And Kepler was a total genius. He must have been a little bit crazy as well, because he went through all of Tycho Brahe's observations and with huge detail. This is before calculus or anything else like that. He then convinced himself that actually the orbits were not circular, but elliptical. And so we have Kepler's laws, and fundamentally, that solved the sort of solar system scale. So that's where we got to in the beginning. Then 1609, 1608, telescopes came to the fore with Galileo and also Thomas Harriot, the Brit. And that then showed the universe had a lot more in it than you could see with the naked eye. You could see stars in the Milky Way, you could see satellites of Jupiter. And so then we had bigger telescopes as technology developed. Herschel's telescope, which is a big reflecting bucket, which discovered Uranus eventually, the first planet to be discovered with an instrument. Then we had the era of the large refractor, which is the Lick 36-inch refractor. Then the era of the big reflectors. This is the Mount Wilson Hooker telescope, 100 inches in California. And this really reigned supreme, used by Hubble, introducing the Hubble-Lemaitre law. And this reigned supreme until it was superseded by the Palomar 200-inch telescope. And this is brute force battleship technology, the Palomar 200-inch. Its mirror was essentially 5 meters across, and it was 24 inches thick, and it weighed 15 tons. So this is a huge piece of mechanical engineering. And as technology developed, people then built lightweight telescopes on nice big equatorial mounts. This is a 4-meter telescope. It's the Anglo-Australian Observatory, but these are built also for Kitt Peak and also in Chile. So this became the 1960s to 1980s generation of 4-meter telescopes. We did a lot of the hard work in terms of our discovery in astronomy. And then more recently, we have the new technology telescopes, the European Southern Observatories, very large telescopes, the VLTs. Now, these are different. They have 8-meter mirrors, but they are on alt azimuth mounts, which means the mount is straight up and down just like you and I. And it goes from side to side and up and down. So you have to track a celestial object on the sky, you have to move it simultaneously in 2 dimensions. Whereas in the equatorial band, you get the declination, the up down bit right, and you just move it left to right. That's all you have to do. So technology had to wait until it was a sufficiently advanced phase that you could do this very, very fine guiding with these new large telescopes. And this set the scale for big telescopes in general. So these are the 4 VLTs. And the next thing we have, which my cursor seems to have not wanted to work anymore, is the Keck telescope. Now, this is effectively a 10-meter telescope, except instead of having a single big gigantic mirror, it's made of segments, 35, 37 segments, each about a meter across, and these join together to mimic a single big mirror. But of course, you realize the edges of these segments have to be aligned to a huge accuracy, far, far better than the wavelength of light. Otherwise, you're just going to get a distorted image. And so again, this had to wait until technology of edge sensors and microcomputers came to the fore before this could be built. And fundamentally, all new telescopes in the future, virtually all new telescopes in the future, are looking at this particular type of design. This will be the future telescope, the European Southern Observatory's extremely large telescope. It's 37 meters across, equivalent size, and it has sort of 800 segments, and it's just enormously huge. And on the picture you can see in front of you, you can see somewhere down here, that's a truck. And so you can sort of see the scale that we're looking at in terms of this. Now, a telescope is really a big collecting area. It's just a light bucket. And a telescope is only as good as the instrument or detector you put behind it, certainly for doing science. And the eye is what one used for a long time. And the eye is a brilliant device. It works in color. It can see low light level, but it can't integrate. It takes sort of 15 frames a second. And that's what, if you can't see it in those 15 frames a second, once you're dark adapted, you ain't going to see it. And so the eye has limitations. Furthermore, you can't demonstrate to somebody else what it was you saw unless you drew it. And so many of the early telescope observers were really skilled artists in terms of their drawing capability. And so the eyeball was the preferred until the photographic plate came along. And this is an 1860 image of Draper with his photographic plate. Now, the photographic plate in those days was about as sensitive as the eye. The quantum efficiency of the eye is not very good, and the photographic plate was no better. But it did 2 things. It could integrate for a long time. So you could open the shutter and you could let the light fall on the plate for 10 minutes, an hour, 5 hours, as long as you could guide the telescope. So it stayed put on the source in the sky, you could integrate. It also provided a record which other people could then look at and decide, was this real or not real? And that's very important in terms of scientific discipline. And then we have the advances in the photomultiplier tube, which have a quantum efficiency of around 10%. The eye is about 1% or even less. And then we finally have the CCD, which everybody has in their camera in one form or own, their camera, which are now called phones, but that's all they are now, the modern cameras. And this is a CCD, which goes in the Hubble Space Telescope. And these have quantum efficiencies of around about 95%. So you can't make them much better than that. So in terms of detectors, in the optical and infrared, we've got about as far as you can go. You really can't make them much better than we can make them now. And so then you have lots of various things that go onto the telescope, the various instruments, spectrometers, polarimeters. I'm not going to go into these, but these are all the things you have to do the science that you need to do. And it all comes under the magic name now of smart focal planes. You put as much technology as you can into the focal plane of the telescope. Also, instead of building your own instrument, nowadays all the major observatories come with massive common user instruments that everybody can use them, and they always work and they're always calibrated, and that's how it all goes. The observatories come with them. This is one of the VLT instruments on the crane. You can sort of see it suspended on the crane like this. It's sort of the size of a small van, weighs about a ton. This is the Muse spectrograph. It has 24 spectrographs in there, plus integral field units. You don't have to worry about what they are. They're just complicated things for getting science out of the light that the telescope grasps from the distant parts of the universe. Also, now we do time domain astronomy by building special telescopes. This is a supernova search telescope in California. Now, beyond the visible, the next thing happened in 1933 was radio astronomy with the Raber dish, or the Raber, or the Jansky sort of antenna. And this is the first radio telescope, which looks like a bunch of wires. And in fact, it was a bunch of wires. This discovered essentially radio emission coming from the Milky Way. And then 1937, we have the Raber, much more looking like a proper telescope, what you and I think of as a telescope. And this effectively discovered individual radio galaxies. Moving on from there, we have the famous down the road from all of us, and particularly you, down the road we have the Jodrell Bank. And this was essentially finished in 1947 to 57, and it was essentially late, vastly over budget. Bernard Lovell was up before the Public Accounts Committee because he'd really blown the money. And everything was just saved from being really disastrously wrong by Sputnik being launched. And Jodrell Bank was the only telescope that could track the Sputnik. And so all of a sudden it was saved. Lord Nuffield stepped in, cleared all the debts, and now we have the Nuffield Radio Astronomy Observatory at Jodrell Bank. And this has gone on to do fabulous discoveries in terms of moving radio astronomy forward. Then we have the 300-foot Green Bank telescope, which is very famous for falling down. And eventually that collapsed. And we keep on having collapsed telescopes these days that are seaboard now just gone. So big radio telescopes don't last forever. However, this one was rebuilt, the glorious magic thing, named after the local senator. It was all political money which built it, but that's how it works. So radio astronomy has a limitation because the wavelength is very long and the dishes aren't very huge. The resolution, the ability to see detail on the sky is not very good. And you really want to see detail. You want to see fine detail in the objects. And there's a way to get around this in the radio, and that's by building an interferometer, which is a bundle of radio telescopes. There's 5 of them here. This is the 5-kilometer set of dishes at Cambridge by Ryle. And this mimics a single telescope of 5 kilometers in diameter. And this gives you, certainly in one plane, much higher resolution. And that's very, very important indeed. Then you can go one stage further. Instead of having a single line, you can build effectively a triangle, and you can move these dishes along all these lines to mimic a big radio telescope effectively of that. This is a very large array in New Mexico in the States. And so resolution becomes very important. We in the UK have a very important instrument called Merlin, which is a multi-element radio linked interferometer headquartered at Jodrell Bank. And this essentially gives you very, very fine resolution detail. I mean, the telescopes aren't even connected together apart from radio fibers, or essentially it's all optical fibers now in terms of getting the data together. And one of the biggest arrays we have now is 63 dishes on the 16,000-foot high Atacama Plateau in Chile. And so this is the ALMA, and this can get superb resolution. And resolution, we'll see, becomes very important when we talk about exoplanets and star formation more than anything else. And finally, in this particular section, we have the SKA, the Square Kilometer Array. The observatory was just commissioned effectively about a week and a half ago. You might have seen on the news when all the nations came together and signed the international treaty. So it's now like CERN. It's a big international treaty, or the ESO in terms of that. This is run from Jodrell Bank, except the dishes are in 2 places. There are what's called mid-wavelength dishes looking like normal radio telescope dishes. These are in South Africa. There are 200 dishes over an area covering 33,000 square meters of collecting area and 150 kilometers apart, looking like a big 150 kilometer dish. And that's equivalent to about 5 football pitches, Man United, Man City size. These are 130,000 antenna in Australia. That's over 100 or half a square kilometer and spaced out over 65 kilometers in extent. And these look more like TV aerial twisty things and wire moves. And that's all they are. These work at low frequencies. And this is the world instrument of the future, the Square Kilometer Array. And as I say, headquartered just down the road from you in Jodrell Bank. Then, of course, you want to go to all the other lengths like X-ray and gamma ray, and you really have to go into space in there. So X-ray and gamma ray astronomy effectively had to wait until space platforms, space detectors came along. Then the infrared came along, and this is the UKIR, the United Kingdom Infrared Telescope in Hawaii, which I spent many a very pleasant time observing and doing a lot of my research work. And then in the submillimeter, which is the wavelength in which I spent most of my time, technology had to come along slowly. This is at the back end of a telescope. This is the Cassegrain focus where there is a detector sitting here. The actual detector is a piece of semiconductor material deep inside here, fed through a window. But the technology is the temperature of the detector is minus 269 degrees centigrade. It's effectively only 4 degrees above absolute zero. So you require a fair bit of technology to do that. Submillimeter turned out to be an interesting way forward for the future. And so 3 governments built the James Clerk Maxwell Telescope, a 15-meter dish on the 14,000-foot summit of Mauna Kea in Hawaii, which I was director for a decade. This is the James Clerk Maxwell Telescope. And one of the major things that developed in terms of instrumentation was this thing called SCUBA. This is the SCUBA array, which made many discoveries, including dusty galaxies in the very early universe called SCUBA galaxies now. And this was the first submillimeter camera. Before then, we just had single pixel devices. And given the fact you've all got megapixel devices on your phones called cameras, you know, a single pixel device doesn't give you a whole lot. This didn't have a many pixels, but also its temperature was 0.1 degrees above absolute zero. And you had to get the detectors as cold as that to make them sensitive to radiation coming from space. And that's a whole different talk in itself, but it's just to say technology had to come along, and in fact, it's major. And this is the instrument that I developed for the JCMT to follow on from SCUBA, called knowingly SCUBA 2, size of a big van, weighs the size of a big van, and this has 10,000 pixels. So in the space of a decade, it went from 1 pixel to 100 pixels to 10,000 pixels. Again, all because of technology. And again, that's a whole different talk in itself. Now moving on to something in the recent phase of gravitational waves. This has been going on the cards for 40 years. This has been developed. It's only in the last few years it's been successful. So it's taken 40 years to get the challenge. When I was first involved with this in the 1980s, and they were 10 orders of magnitude away. That's 10,000 million times away from where they had to be in sensitivity. So in 1980, they had no chance whatsoever. But by pushing technology, they've got better and better and better. And now they're detecting gravitational waves. So it's absolutely fabulous to show that advancement that's gone on there. I'll just go back to that one slide. This is, it's called the gravitational wave interferometer, which I won't go into, but it has waves in that direction, a line in that direction. These are vacuum tubes with mirrors at the end, and you shine lasers down the vacuum tube, you recombine them here, and if the lasers change, it means a gravitational wave may have come through the apparatus, but that's all I'm going to mention about that. Now, let's see if this video works with sound. Can you hear the sound?
Yeah, we can hear that fine, thank you.
Okay. That's the gravitational signal, which is on here by the 2 gravitational wave detectors. This is the gravitational wave signal translated into a sound wave. And that chirp you hear at the very end is effectively 2 black holes colliding. And it's just fantastic. As they collide, they emit gravitational waves. It all happens in the last second. In the last 0.2 of a second, the 2 binary black holes are orbiting each other at around 20 to 30% of the speed of light. I mean, that's just incomprehensible. when they collide and they emit gravitational waves, there's enough energy in, there's the same energy in the gravitational wave being emitted at that moment as all the visible stars in the universe. It's just phenomenal. And so that's the whole challenge of gravitational waves. So it's a whole new field to watch out for. And 2 years after its first discovery of gravitational waves, they had this new object, GW1 170817. And the important thing about this was they had an additional Virgo detector, gravitational wave detector available. That pinned down the area of sky significantly. It was still a whole big chunk of sky, which is very hard to figure out. But the Fermi Gamma Ray Observatory was also available at the time. It detected a gamma ray flash. It then narrowed down the piece of sky. So optical infrared telescopes within 24 hours found this gravitational wave source from the gravitational waves and the gamma ray flash. They found it was a whole new phenomena, was two coalescing neutron stars in a binary system. This was a kilonova, which explains short gamma ray bursts, which for a decade had been a real new idea for astronomy, and people didn't really know what they were. People thought there might be neutron stars, but nobody had proved it. This experiment definitely proved it. And this shows the need for a wide field temporal follow-up telescopes. And this is going to be the Zwicky telescope facility with 47 square degrees of field of view. So that's going to be absolutely fantastic. Let's now move on quickly to observatory locations. Well, when Galileo started off, he was at sea level on the Venice Plaza, and so that wasn't very good at all. Then people started putting things in towns, and then when light pollution came on, they moved them away out of town, and then even then the light pollution was so great. So people went and put them in the countryside. This is what the UK did in the 1960s, except it was still at sea level, so that was pretty pathetic overall, really. What you really want to do is get to a high mountain, get up there. This is the Siding Springs Observatory in Australia with the Anglo-Australian telescope. And this looks fabulous, except from one thing wrong with it. It's full of green, which means it's far too low, really. And the optical seeing at this site has never been really crystal clear at all. But observatories get built in blocks because once you've built an observatory fundamentals, then economies of scale say you build more telescopes there because they can share the same infrastructure. And this is Kitt Peak in Arizona. Again, it's only about 7,000 feet high. And so it's not one of the best sites at all. What you really want to do is go high. So let's go to Hawaii, not Waikiki Beach, rather Mauna Kea. 14,000 feet high summit, not anything green in sight. Can snow any time in the year, and here you have a panoply of major 8 and 10 meter telescopes, the Keck, the Subaru telescope, James Clerk Maxwell in the valley. And so this is, you now go to really very special and very expensive observatory sites. This is La Palma, the fabulous caldera in the Canary Islands. And this is one of the most barren sites at all. This is the Atacama Desert with the European Southern Observatories VLTs. So these are the full VLTs. This is the Vista telescope, which I'll talk to you about later, which I had to deliver to ESO at one particular point. Now, we shouldn't forget the amateur scene, and you've already mentioned astrophotography, and actually technology has helped the amateur scene really quite remarkably. You can buy ready-made domes now that mostly are waterproof. You can buy fabulous telescopes of a whole range of science, and the only thing that's limited is how much you can afford to pay for it. They're just fabulous things. Then you can also buy cooled CCD cameras, which gets on the professional market. So astrophotography is doing really, really fabulous with amateurs. And there's a whole pile of software and apps available. So amateur astronomy is really, really doing well in terms of this. But of course, also you can fly balloons to do astronomy on. You can also fly aircraft. This is the Kuiper Airborne Observatory, the 36-inch telescope inside. And this is the Sophia telescope with a 2.5 meter inside. I'm not going to mention these at all, just to say they are stepping stones to what you really want to do, which is get into space, except space is expensive. Hubble Space Telescope revolutionized what we know about the universe. This is John Grunsfield's photograph of the refurbishment, the last refurbishment of the HST before the shuttles were essentially binned. And the future will be the James Webb Space Telescope. This will take over from Hubble. It works in the infrared, the mid-infrared, and will be in a special position. It'll be about 1 million miles beyond the Earth in what's called the Lagrange 2 position, which is a stable orbit. That's all you need to know about that. And it'll sit there and it will observe the universe. And it's a really amazing thing. And this is a video which shows you it gets launched and it has to all fold up to fit an Ariane 5 launch module, the fairing. And then as it goes into space and as it's traveling to the 1 million miles away, the Lagrange point, various things have to happen. First of all, the sunshades have to come out because you've got to protect this telescope from seeing anything like sunlight or earthlight for that matter. So these sunshades are made of Melinex mylar, aluminum foil. They're very thin. There are 4 of them, and you have to expand them out. Then you have to separate them so they don't have physical contact with each other. So you remove the thermal conductivity, and these will all point backwards so the sun can't shine on any of the mirror. So all this is happening while the telescope is flying to its million mile away orbit. And once it's there, it's fly and forget because you can't do any servicing on this. So all of these bits have to work. There's a secondary mirror coming out, and there's the primary mirror folding out. So all of these things have to work robotically. So this is a real high-risk telescope which is going to on. And if you look on the web, there's a YouTube called From Northrop Grumman, All You Need to Know on the JWST, which tells you all about this in more detail than this. And that's well worth YouTubing to get to know that. Now, we also do multi-messenger astronomy, which is a fancy name to say we use things like neutrinos. This is the Ice Cube experiment, which has detected neutrinos from a blazar, an active galaxy, which I won't go into. But just to say, astronomy is now gone into astroparticle physics, is a new name in the buzzword of astronomy. We also can do astronomy underground in the realm of astroparticle physics. This is a mine in Cleveland, in North Yorkshire, a potash mine. The mine. And this is the access to the computer. Is that my sound going or?
Hang on, Ian. Rajinder, can you mute your microphone, please? Thank you.
Okay, we'll keep going. And so this is dark matter in terms of trying to detect particles in the universe. Right, well, going nearer to home, the solar system. The solar system, all the bits in the solar system are sufficiently clear. You can send objects to them, or you can even send a person to them. So we've been to the moon, we've trampled all over it, we've brought things back from it. This is a lunar sample from the first Apollo mission, and I had to take this wrapped up in a silver paper in my pocket from London to Newcastle because there was no safe way to do it in those days, and nobody would insure it. So it was a question of take it and hope nobody robs you. We also can see what we've left on marks on the moon. This is from the Lunar Reconnaissance Orbiter, and this is Apollo 17, the last mission. And you can see the descent stage. You can see where the rover was left and parked. You can see the moon buggy tracks. You can see astronauts' tracks. And so we've left our mark in terms of our nearest neighbor, the moon. But of course, this is where people really want to get to in terms of Mars. And this is a fabulous photograph from a Mars orbiter looking at where we all want to be. And there have been lots of missions to Mars, and there are going to be lots more missions to Mars. We have the Curiosity rover, which has been trundling around there since 2012, doing fabulous things, digging at the rocks and having a look at what they're made of. And in the very near future, on February the 18th, which is less than 2 weeks away, the reconnaissance orbiter will get there. And it's called Perseverance. And this has got an amazing descent sequence. And there are bags of things on YouTube, and you'll see it on TV in the next 2 weeks. But if you want a good look beforehand, just do a YouTube on the Perseverance orbiter getting on there. And it really is fantastic. It's 7 minutes of sheer sort of knuckle biting. Will it work or will it not work in terms of parachutes and rocks and everything else like that? If it all works, this is Perseverance on the surface. And this will attempt to do some bio experiments. We know there's water hidden under the surface of Mars, and this will try and look for essentially some semblance of life on Mars. Now, this is, of course, fabulous view of the planet Saturn, and this was visited by the Cassini mission, and this is the Huygens probe, which landed on the surface of Titan and discovered many, many things about the surface of Titan, including, in fact, it's not very hospitable. And looking back on Titan, it also showed Titan has lakes. This is sunlight light reflecting on a hydrothermal lake on the surface of Titan, indeed. One of the most amazing experiments recently in the last decade has been the mission to the Rosetta mission to the comet 67P. I can never pronounce the Russian's name, so I don't even give it a try. But 67P, this dumbbell-shaped asteroid which rotates, and this was just amazing. And it almost worked, putting a lander on the surface. This is the Philae lander about to land on the surface. And if only the German harpoon had worked and kept it anchored onto the ground instead of it bouncing and bouncing all around, it would have been really, really spectacular. It almost worked, but nevertheless, some fabulous photographs. The Japanese went one better. They sent Hayabusa 2, that's the second of their missions, to the asteroid Ryugu. And this effectively worked absolutely flawless. It's a peculiar shaped asteroid, and this is the surface of it. And they had a probe which blasted a hole in the system, collected the debris from the hole, and then trampled its way all the way back to Earth. And they've now been retrieved. So we now have asteroid samples. Okay, changing gear now to what can go on in the solar system. This is a coronagraph of coronal mass ejection, huge flares of high energy particles blasting out from the sun. Now, there are many, many, many of these on the web, and there are far better and newer ones, but this is one of the very, very original ones from 2001. And it shows what can happen when the corona mass ejection essentially sends particles towards the observer. See that noise on there at the time? That will charged particles hitting all the CCDs. This means they can also hit satellites in orbit around the Earth, telecommunication satellites. They can also cause real problems in terms of telecommunications, and really coronal mass ejections and space weather has become very important. It's so important, it now features on the UK government's risk register. But then again, so did the global pandemic, and look what happened there. But nevertheless, it's on the risk register now. So we know a lot more about the sun and what goes on there. So overall, we've come a long way. We know a huge amount about stellar evolution. We know more or less how stars form. We don't know precisely how they form, but we've got a very good example about that. We know how they evolve. Stars like the sun will swell up. It's about halfway through its life now at 4.5 billion years. It'll swell up. It will become a red giant. It'll blast out the layers off. There's a planetary nebula probably, and condense down to a white dwarf, which is the mass of the sun and the size of the Earth, which means the density is very, very high. It's about 1,000 kilograms per cubic centimeter, and a sugar cube is about a cubic centimeter. So it's about 1,000 kilograms or a ton in a sugar cube. So you take your Nissen micra, squash it down into a sugar cube size. That's the density of a white dwarf. For more massive stars than the sun, maybe 5 or 10 times the mass of the sun, they swell up very rapidly and become supernovae and explode. And they blast the outer layers away, and they may leave a core called a neutron star. This also has the mass of, let's say, the sun, but it's only about the size of a large city, maybe 15 kilometers, 20 kilometers across. This density is absolutely enormous, and it's about 10 to 11 kilograms per cc. So effectively, you end up with something like 100 million Nissan micras squashed into your sugar cube, which is really very, very hard to sort of figure out. Another way of doing it, it's 250,000 Boeing 747 jumbo jets in a sugar cube, if that makes you feel any better in terms of that. We also know that these supernovae for the very massive stars can just explode and leave either a black hole or nothing. But they enrich the universe and produce all the heavy elements that life needs to keep going. So we know about stars. Galaxies, we know all the big massive galaxies now have supermassive black holes at their centers. We're not altogether sure how they got there, but we know a lot about galaxies. Galaxies are building bricks of the universe, certainly in terms of that. And cosmology, well, 20, 30 years ago, we were really quite smug. I mean, we thought we understood all of cosmology. Then all of a sudden, to our chagrin, we had dark matter and dark energy. And astronomers realized actually we really understood only 4% of the observable universe, which is really quite embarrassing in terms of that. Now, I'm not going to talk about cosmology tonight at all, but essentially, we do have a very good overview of what happens in the beginning of the universe from 10 to the minus 32 seconds, which is just hard to imagine. But at 1 second, then that's sort of reasonable physics. The temperature is 10,000 million degrees, and we understand what really goes on there. It's sort of doable physics. And then the universe expands. But again, I'm not going to go into cosmology, but we know an awful lot, but we still have no real idea about dark energy and dark matter, and that's about 96% of the observable universe. So that's still embarrassing. But we do have new fields in astronomy coming along. The search and discovery of exoplanets. This is one of the big new things over the last 20 years. This is the Kepler telescope, orbiting telescope, which made the major discoveries. Then there were HARPS and HARPS North on the ground-based telescopes doing occultation experiments. And they came up with these thousands of new exoplanet systems. I mean, and they're all really exotically different. This is one particular example I've picked in this whirlwind tour of the universe. It's called the TRAPPIST system. And this is what it looks like. This is the solar system, our solar system. See the central little bit there? That's been blown up to get the TRAPPIST system, which essentially is a very, very small red dwarf star. It's only 70 times the mass of Jupiter. It's really cool and it's really small. And it has this bundle of planets, a little about Earth size, but 3 of them in the nominal habitable zone for the TRAPPIST system. And so exoplanets and astrobiology is one of the key things essentially for the future. In the future, what we hope to do is image planets directly going around. This is the ESO VLT, which we saw earlier on, plus an interferometer measurement of it. And this is the star in the center with the coronagraph. And this shows a planet in the stages of formation in the dusty disk surrounding the star. So this is where we want to be in the future. Astrobiology, again, in the last 30 years, we've discovered all about astrobiology. Once we learned about extremophiles and the huge amount of different extreme areas of the Earth in which they will exist and they can live, all in any space as well on the space station. So we realized that the universe could well be populated, certainly the solar system could be populated by very primitive life, bacteria. And so the question of are we alone, I'm sure the answer is no, we're not, but there might be all bacteria. But nevertheless, it's really a fascinating subject, which has enormously grabbed the imagination. And now it's a whole dynamic subject all in itself. Now, in another year's time, ExoMars, the European mission, will launch. The second part of it will launch with the Rosalind Franklin rover, which was named last year by public acclaim. And in the solar system, there are actually a lot of new places where you think life might be there, either in the substrata of Mars or in the oceans of Enceladus, the moon of Saturn, which is what we're looking at now. And we know there are hydrothermal vents, which could easily have the conditions which we see on the Earth to contain extremophiles and early primitive life in terms of that. And looking for planetary systems, this is a Keck image of planets going around a star. This is quite an amazing image. But nowadays, with the future large, extremely large telescopes, we want to be able to look at these planets and take spectra and say, can we detect the requirements for life, like oxygen or particular elements in the atmosphere that are only produced by life-forming organisms? And so this is again for the future, but searching for signs of life is going to be very important. Now, also, the whole game of astronomy, observing, has changed over the years. And when I first started going off, you applied for telescope time, you got your 4 or 5 nights, you went half around the world, You got snowed out, you came all the way back, you had no data. And this is a real weather lottery. And when I was director of the James Clerk Maxwell Telescope, this was really a shame because what it meant was some of the highest scientific programs were going out to get time and were weathered out. And some of the lowest prior scientific project programs, they were still good programs, but they weren't the highest priority. They would get 5 brilliantly clear, superb nights. And you thought this just can't be right in terms of value for money. And so in the end, I managed to put in for science ranked, weather dependent, Q based observing. So what got observed at the telescope depended upon how high a scientific ranking it had got, what the weather was like on that particular night, and then it will be scheduled and done. But it required a huge amount of software to be able to do that, and a huge amount of confidence by the observers to let other people maybe do their observing rather than them doing their own thing. And so that was a major change. And nearly all the major telescopes now use Q-based observing rather than people going out for 4 nights and at the weather lottery. But of course, one of the things is, has this made ground-based observing more like space observing? When you Hubble Space Telescope, you send off your program, you get your time, and the Hubble Space Telescope will observe it, and you sit in your office, and your data comes back to your computer. And that's essentially also a lot of what happens in ground-based astronomy now. So it's a big changing scene in terms of the future and what happens. But it's also far more efficient in delivering taxpayers science and value for money. But we've come a long way and there are still limitations. We've got massive ground-based optical infrared telescopes, huge flux gathering capability. They can see to the edge of the observable universe. We now also have diffraction limited imaging with adaptive optics, which I haven't talked about at all because it's just too hard to fit in. But all these telescopes have small fields of view. So to look at the big sky, you need different telescopes. You need wide field astronomy and to do surveys. The first thing that really came on the scene was the Schmidt telescopes in Australia and Chile. These took big photographic plates, and I've got one here which you might just be able to see in terms of if you, well, those who are on the same page as me can see them. They're about 20 centimeters by 20 centimeters in a photographic plate, and so they work really quite well. Then this is the Vista infrared camera and telescope, which I showed you. Now, the interesting thing about this, those of you who are aficionados of telescopes, this thing is an F1 telescope. It's a cube. It's no longer long and thin like you used to see. It's F1 because we can now produce F1 mirrors, and that gives you a much wider field of view. It's got a 67 megapixel infrared camera, and it produces beautiful images like this image of the whole Orion complex. Absolutely fabulous. So this is wide field astronomy. If we move on in terms of what you might call the big sky, this is the future. The Large Synoptic Scale Telescope, Survey Telescope, now being renamed the Vera C. Rubin Observatory. It's got an 8-meter mirror, approximately 8 meters mirror in there. And again, it's F1, it's a cube. It's absolutely massive. It's enormous. This is just the camera in the focal plane for this. And this is the detector. It's a 3.2 gigapixel array of CCDs. And what you see there is the image of the full moon. This is almost 45 full moons worth in one go. So this will absolutely survey the sky to a real huge depth, and it will just produce an enormous amount of data. And in fact, that brings us into the data explosion and the era of big data, which we are now in. The Hubble Space Telescope takes 2 gigabytes a day, so it's 200,000 bytes a day. Vista, the infrared telescope I talked to you about, has a data rate of 315 gigabits per night, 110 terabytes a year. The LSST is 20 terabytes per night. I mean, these things are just, once again, the petabytes and terabytes, it's like, don't forget the gigabytes, 10 to the 9, the terabytes is 10 to the 12, petabytes is 10 to the 15. I think it goes to quadrillions or whatever, 10 to the 18, but just unbelievable to sort of figure out what's going on. And so this is 8 petabytes a year, huge amount of data. And the square kilometer array running from Jodrell does 1 petabytes per second. The internet today seems to be doing something like 30 terabytes per second. And that tells you one of the things about the SKA phase one. It gathers data so rapidly, it hasn't got a hope of transmitting that data away from the site. And so what happens is there's a huge amount of pre-analysis which goes ahead on the site. And only when this has been reduced to by about a factor of 1 million can the data be transshipped back to, say, the UK and Jodrell Bank. So data becomes so high, you can't ship it around the world. You have to crunch it in site, in situ, and then move it on. It also means you've no hope of creating an archive for all the raw data. Raw data has to be then analyzed right away on site and sent off. And the computers on this can only just about keep up with the data rate coming in. So it's a huge data rate challenge. And this just gives you an idea of it's just big, big data. And big data is very important. And the UK government is putting a lot of money into studentships and postdocs for analyzing big data, including a bunch in astrophysics to do that. So finally, coming into big data means artificial intelligence and how you then can work through the data rates that you've got, and the production of neural networks, which are now used to do many things, looking at gravitational lenses in the universe to show the existence of dark matter, analyzing transit experiments, looking for exoplanets, doing it by artificial intelligence rather than the human eyeball, and also trying to see if they'll work on gravitational wave detection. So neural networks and AI is now a big, big thing in data computing and analysis. So it's also astronomy is changing the paradigm essentially with all this data, because now people can get involved in astronomy by working at home with SETI at Home project, for example, and generally citizen science, because there's so much data out there now that astronomers themselves can't analyze it all. And so the public can get involved with citizen science, Universe Zoo, Zooniverse, and Galaxy Zoo. And that actually has a difference for the research student. For the research student, life has changed. It used to be a pedagogy, how to solve an astronomical problem. And you either went out and got your own data, or you sat and you got data sent back to you, but it was not a huge amount of data. Now, many of the PhD problems for research students, it's how to solve a big data problem, because many of the big questions require big data and big data coming back. And so astronomy has gone from essentially the human eyeball looking at the sky and drawing constellations as the Babylonians did, to horrendous big data problems with massive computer and cloud computing requirements. So things have changed enormously, and we're learning a huge amount more. But don't forget, we still don't understand 96% of our observable universe. Thank you.